Hi, I'm Ollie Long, a PhD student at the University of Southampton, and I'm going to be talking about progress towards self-force calculations of the scatter angle in hyperbolic orbits, and this is work I've done with my supervisor Leor. So first I'm going to talk about EMRIs and LISA. So an EMRI is a supermassive black hole which is orbited by a compact object, and for LISA these have mass ratios 10 to the minus 5 to 10 to the minus 7. These systems have about 10 to the 5 orbits in the LISA band, which corresponds to about a year of observation time. So the signals from the EMRIs are weaker than the instrument noise, but the large time that they spend within the LISA band gives a large cumulative signal-to-noise ratio, so that we can see them in the noise plot here. So now let's move on to expanding in the mass ratio. So we can expand quantities such as the full EMRI metric here in terms of this mass ratio eta. So the 0th order is just the background metric, which is just Schwarzschild or Kerr, depending on the central black hole. And then you have these perturbed metrics, and here we've gone to 2nd order. So for LISA, 1st order is sufficient for detection, but 2nd order is needed for parameter estimation. Now I'm going to talk about how we calculate these with metric reconstruction. So first we start off with a Weyl scalar, which is a curvature scalar, so it describes the curvature of the spacetime. Now this solves the Teukolsky equation, and this can be done for spin plus or minus 2, hence the plus and minus here. And once we have this solution, we can take a 4th order derivative in an operator and get to the Hertz potential. Now this Hertz potential itself is a solution of the adjoint Teukolsky equation, which is just the Teukolsky equation with flipped spins. Now once we have this Hertz potential, we can get back to the metric perturbation by a 2nd order differential operator. Now this has been done to 1st order for generic bound orbits in Kerr and to 2nd order for quasi-circular orbits in Schwarzschild. But what about scattering? Well, first we'll talk about the motivation. We can use self-force information to give information to other calculations, such as the self-force is valid here, but it can give information for the post-Minkowskian method, which is here. We can also use it to compare with scatter amplitude calculations, which are quantum-style calculations. Another thing we can do is use it for calibration of effective one-body methods of modelling, and this is particularly useful for the strong field regime, as even at low energies of 1.1 you can see that the scatter particles penetrate well below the ISCO. So now we'll look at the Teukolsky equation. The master Teukolsky equation is written here, and as you can see this psi depends on t, r, theta and phi. So we can expand this. We can expand the spin plus or minus 2 fields in terms of spin plus or minus 2 spin-weighted spherical harmonics, as shown here. And when you do this, all of the angular part of the equation is described by the spin-weighted spherical harmonic of the mode, and then the time and radial parts are described by this equation here, which has been written in Eddington-Finkelstein coordinates, as that's the simplest form. So now, once we know the Teukolsky equation, how do we solve for it? Well, here we have a 2D numerical grid, and we will use a 2D finite difference scheme on it. We have initial conditions on the null rays, the initial null rays of constant u and v, and it doesn't really matter what we put here. But for vacuum, we need an initial pulse or something to seed the calculation. So consider we want to calculate this point psi naught given these 3 other points. We can use the other points and these functions h, big H, and these depend on the grid spacing, little h, the mode that we're currently trying to calculate, and the radius. And so you can calculate points iteratively and cover the whole domain of the 2D space. So when you do this, we find that there's a problem with divergent modes. for s equals plus 2, there are exponentially growing modes, and s equals minus 2, there are modes that grow as t to the 4. And if we look at asymptotic solutions of the Teukolsky equation, we can see that at the horizon, there are exponential solutions for s equals plus 2, and at null infinity, there are t to the 4 solutions for s equals minus 2, which is exactly what we see in the plots. So these are usually removed by physical boundary conditions, but as we don't apply physical boundary conditions in our method, this doesn't work. But both of these terms originate from the time derivative of the field, so we can just eliminate that instead to get rid of the problem. So how do we eliminate that? Well, we transform to a Regge-Wheeler type form. Now, to do that, we use a time domain version of the Chandrasekhar transformation, which is shown here. So if phi is a solution to the Teukolsky equation, x is a solution to the Regge-Wheeler equation shown here. And as you can see, this has a very similar form to the Teukolsky equation, but without the single derivative terms. And as it doesn't have the single derivatives of u and v, that means it doesn't have the single derivatives of t. And if we solve this Regge-Wheeler equation and transform back to the Hertz potential, using this transformation, then we get the results here. And you can see that there's no t to the 4 growth as would be expected from the Teukolsky equation, as this is s equals minus 2. There's just the normal quasi-normal mode decay and then the round off error. So now let's talk about putting a particle into the situation. The Teukolsky equation is sourced by a delta function and 2 of its derivatives. So the most general solution for this gives a string singularity that goes from the central black hole through the particle off to radial infinity. But there is a degree of freedom in this solution, and you can use it to get rid of some of the singularity. So you can use it to get rid of either between the particle and the central black hole, or the particle and radial infinity. But there's a trick you can do where you take the nice parts of both fields and put them together. So technically you're solving for 2 different fields inside and outside of the particle. And if the particle is moving, as is the case for a scatter orbit, then the domains of the fields change with the particles. So it's just the instantaneous particle radius that they apply to. So now let's define jumps in the field. These jumps are defined as the difference in the inner field and the outer field as you tend towards the radius of the particle. For the jumps in the Weyl scalar, we can obtain this directly from the source Teukolsky equation analytically, but for the Hertz potential, we have to solve a first order ODE. And the source of this ODE, as you can see here, depends on the jumps in the Weyl scalar. So once we have the jumps in the Hertz potential, we can get the jumps in the Regge-Wheeler variable using another first order ODE. And as you can see, again, the source of this depends on the Hertz potential. So they all depend on each other. And for the circular orbit, we can determine these jumps analytically. So let's have a look at that case. So we now have a different finite difference scheme because we now have a world line that goes vertically through the domain. And this changes the scheme as we have the original vacuum part before, which is unchanged, but we also have these j functions which apply to points near this world line due to the fact that on one side of the world line you're solving for one field and one side the other, and the scheme needs to take account of this, which is why it depends on the jumps in the field. So now if we plot these solutions, you can see we have this initial junk data at the beginning, and this is just due to us not using physical boundary conditions. Then this decays, and you can see with the Regge-Wheeler solution, it tends towards the analytic solution, which we have because this is a static mode. But the Teukolsky equation decays, and then there is the growth of this t to the 4 mode. So the unstable modes are still present in the non-vacuum case for Teukolsky, but again they've been removed by the Regge-Wheeler method. So now let's talk about scatter geodesics. So we have several parameterizations. We have the energy here and the angular momentum. So the constraints on this is the energy must be greater than 1, and that for a given energy there is a critical value of the angular momentum, and the angular momentum must be greater than this, otherwise the particle will plunge into the central black hole. We also have another parameterization with eccentricity and semi-latus rectum, and for this, for scatter E must be greater than or equal to 1, and again there is a critical value of P for a given E that P must be greater than for it to not plunge. Now in this parameterization there is a useful quantity here, chi, and this chi is useful because it is bound for r equals infinity. So it's bound between minus chi infinity and plus chi infinity, where chi infinity is defined in this equation, the limit that r goes to infinity. We have a third parameterization, which is the velocity at infinity and the impact parameter. Now, the impact parameter is just the point of closest approach to the central black hole if the central black hole had a mass of 0. So now let's have a look at the scatter angle. The scatter angle is defined as the total accumulated azimuth angle minus pi, so displayed here pictorially, and we can expand this in terms of the mass ratio. So here we have the 0th order, which is just the geodesic value, which we know analytically, and then here we have the first order correction. So to get this, we can solve the first order self-force equations of motions for fixed velocity at infinity and impact parameter, and we use these as fixed as they are invariant, as they are both defined at infinity. Now if we have a look at the form of the equation for the correction, we have here these a and b's which just depend on the parameters of the orbit. We then have this ft and phi, which are self-force components. Now these come from the fact that the motion is no longer geodesic, so these are related to the proper time derivatives of the energy and the angular momentum of the orbit. Also, as part of the calculation, we have this a and b, which depend on the orbit and on chi, but these are known, so we can easily integrate these against the same self-force components that we integrated for in the other terms. So now let's talk about jumps in the field. They are defined the same as before, so the Weyl scalar again can be obtained analytically from the Teukolsky equation, but the jumps in phi and the Regge-Wheeler variable must be obtained from ODEs, given here, and this can be done in several ways, as we can't do them analytically. We can do them analytically, however, for the large R limit, so we've got the asymptotic solution here. We can also do it numerically, and we have done this in a couple of ways. We have solving this ODE directly numerically in Mathematica, given by the solid lines. We also know the homogeneous solution to this equation, so you can get the solution via the particular integral of here. And as you can see, these two methods agree well. So now let's talk about the actual evolution code. We have a world line now that moves not just vertically through the domain, so we need to take account of this. Again, we just have the vacuum solution plus different terms that depend on whether the cell is near the world line or not. And for these we have 4 types of cell, and these depend on where the particle enters and exits the cell, and we have 4 kinds of cells that this relates to. So to summarise, EMRIs are important LISA sources. The 1 plus 1d Teukolsky equation is numerically unstable without boundary conditions, but this can be resolved by transforming to a Regge-Wheeler variable that removes the numerical instability that is ceded by the boundary conditions being non-physical. And also, so we can use self-force scattering results to inform other modelling methods outside of the EMRI regime. Thank you for listening.